Okay, today we're going to talk about square roots, and we're going to look at square roots that have rational square roots. We're going to look at simplifying radicals, and we're going to look for decimal approximations of irrational square roots, which we don't usually do that very often. We tend to want to keep our numbers as exact as possible, so we don't usually approximate, but you do need to kind of get an idea of how to do that. Okay, so let's start with some definitions. If a squared is equal to b, then a is a square root of b. And if you think about that, if I have a square, the whole reason why we say square or square root is think about a square. The thing about a square is the sides are the same. And if I multiply those, it's going to give me the area, which we're going to call b. So that's how they got the term square root. So you have a square and both sides are the same. So that's where they got that term from. So basically a square root is the number that you would multiply by itself to get the new number. Okay. For all positive real numbers A, every positive real number A has two square roots, a positive and a negative. When we use this symbol here, we're denoting the principal square root, which is the positive. Okay, so if I just see something like this, the square root of 4, generally I'm looking for positive 2. If I want to know what both roots are, they'll put a plus and a minus in the corner. Okay, so for all intents and purposes, if we're just looking for a square root, okay, just the positive, unless the directions specifically say give me all square roots or both square roots, okay? 0 has only one square root, which is itself, because 0 times 0 gives you the square root of 0. All right, so we have a couple properties here. First is the product property of square roots. And basically what that says is for any negative real numbers a and b, if I have a number that I'm taking the square root of, I can break it apart into factors. And the type of factors I'm looking for are perfect square factors. So we want to break apart into perfect square factors. You might be saying, well, what is a perfect square factor? Okay, so perfect square factors are, I'll write them up here, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, and so on. So 2 times 2, 3 times 3, 4 times 4, 5 times 5. You get the idea. What you want to do is you want to break it apart using these factors. So it helps if you know the different rules of divisibility or how to figure out these factors. So you're going to have to do some thinking here. So let's look at an example here. I want to find the square root of this number, but I can't use my calculator. Okay, and back in the day, we didn't have calculators. So I need to break it apart. So here's a hint right here. The last two digits, if the last two digits of the number are divisible by 4, that tells you that the whole thing is divisible by 4. And since 4 is a perfect square, that works out well for us. So I'm going to take out the 4. So I have 2304. I'm going to divide that by 4. So that's 5, and that's, I don't know, 7, 571, I think. I'm probably wrong. 576. I knew I was wrong. So this is going to be 576. Okay. And then I say, well, can I break this 576 down even farther? So let's look. If I add this together, I get 11 plus 7 is 18. So it tells me it's divisible by 9. So then I just do 576 divided by 9. And that's going to give me, let's see, it's a 6. 36 is going to give me 64. Ooh, look, 64, perfect square. 4 is a perfect square, 9 is a perfect square, and 64 is a perfect square. So what I'm allowed to do using this rule is I'm allowed to break them apart. And I can say, well, the square root of 4 is 2, and the square root of 9 is 3, and the square root of 64 is 8. And if I multiply those all together, I get 48. Okay, so I found the square root without theoretically using my calculator, at least not using the square root button on a calculator. Okay, so this is something that you're going to be able to know how to do. Let's look at another one. If I have, this one's easier, 225. Obviously, if it ends in 25, it's divisible by 25. So that's going to be the square root of 25, and that would be 9. 9 times 25, both perfect squares. So I get 5 times 3, which is 15. So the square root of 225 is 15. Okay. Another property is the quotient property of square roots, and that basically says that if you have a fraction or a division, because this represents division, you can break it apart just like this, or you can put it together just like that. So let's look at some examples. So here I have plus or minus. That tells me that I want both the positive and negative factors. So I'm not going to worry about that until I get to the very end, and I'm just going to make sure that my answer has plus or minus in front of it. So this rule says that I'm allowed to break this apart. So I have 144, which I know the square root of that one. You should also. And these two. So square root of 144 is just 12. So I'm going to put my plus or minus there. Now this one I need to break apart. Luckily, I know it's divisible by 25. And if I divide that by 25, I get 1, 2, and I lost my place. 1. You get 121. Okay, which, oh hey, 121 happens to be the square root of 11. So I get 25, square root of 121. That's 5 times 11, which is 55. So there's that one. Okay, so being able to break them apart. What I could have also done, which I don't think I could do with this one, but if I had a fraction like this, I would probably want to simplify the fraction, if at all possible, first. Then I have smaller numbers to deal with. Okay, so those are two properties. We have the product property of square roots and the quotient property of square roots. All right, so we talked about rational numbers, and we said that rational numbers were numbers that could be written as a fraction of integers. And as decimals, they're either going to be terminating or repeating. So irrational numbers are the opposite, or they're not rational, which means they cannot be expressed in the form a over b. They can't be written as a fraction of integers. They also can't be written as a terminating or repeating decimal. So the most famous one is pi. And we know that pi doesn't repeat or end, at least not after a billion or so digits. So those are irrational, and there are other irrational numbers. And we'll find that when we take the square root of a number that's not a perfect square, we usually end up with an irrational number. Okay, we're going to be looking at getting exact numbers here. And what you need to remember is with an irrational number, the decimals are rounded. Okay, so when we talk about 3.14, that's rounded. Okay, so it's not exact. I mean, it's pretty gosh darn close, but it's not exact. So when we're talking about irrational numbers, we still want to have an exact number if at all possible. So let me give you an example here. If I have 75 and I take the square root of that, 75 itself is not irrational, but the square root of 75 is. If I plug this into my calculator, I get this. And your calculator might take it farther, but this is as far as mine went. So that's what it tells me is the square root. However, if I take this same number and I square it, it's going to give me this. Okay, so it's not an exact number, okay, because it was rounded. So if I want to find this, simplify it, but have it as exact, I have to keep it in radical form. But I can still simplify it. So if I simplify this, I know that I can take out a 25 and a 3. Square root of 25 is 5. Square root of 3 is just square root of 3. This is still an exact number, and it's this simplified. Okay, so that's what we're looking at, simplifying these numbers without changing them to decimals, because decimals are not going to be exact for these. Let's look at another example. If I have 2 times the square root of 112, 2 stays out front, I can factor out a 16 out of this, and it's going to be 16 times 7. Well, 16 is a perfect square. 7 is not. So that's going to give me 2 times 4 times square root of 7, or 8 square root of 7. So this is simplified, and it's still considered to be an exact number. So that's what we like to have, is exact numbers. So there's going to be times when you will solve a problem and you'll leave it in radical form. If it's a word problem, usually what we do is we end up changing it to a decimal and then rounding it. Okay, but if it's not a word problem, you want to keep it exact, so you're going to just simplify it that way. And we have another property. It's called the property of completeness. And it says that every decimal number represents a real number, and every real number can be represented as a decimal. Okay, so every real number can be represented as a decimal. Okay, every decimal number represents a real number, and every real number can be represented as a decimal. But, it's a big but not necessarily as a fraction. And you need to remember that all rational and irrational numbers are real. So every number we've dealt with up to this point in your life has been a real number, okay? And we're going to continue with real numbers. Complex numbers have a real and an imaginary part. You don't get to that until you get to Algebra 2. So you just need to remember that just because something is irrational doesn't mean it's not real, okay? So rational and irrational numbers are real. So let's look at our proof now. It says express as a fraction in simplest form. Okay, so this is kind of easy. 8/10, which is equal to 4/5. Piece of cake. 2 and 15/100. Now we want to keep this as improper. So improper fractions are simplified, more simplified than mixed numbers. So if I have a fraction, I don't want it as, and I simplify it, I don't want my simplification to be a mixed number. I want to keep it as an improper fraction. So to write this then as an improper fraction, I look to see what's the last place value, and it's the hundredths place. So I'm going to have 100. Well, this is 215 hundredths. Okay, I can just drop that decimal. And then from here, I can simplify it. And that's what I'm going to have, 43/20. This one, we looked at these yesterday, or the last lesson. So if I have n is equal to 0.7, I would do 10n is equal to 7.7. I would subtract my n. I get 9n equals 7, so n is equal to 7/9. Okay, that one we worked on the last lesson. Same with this. We worked on these the last lesson, so I would have, this is equal to n. I would have 1000n is equal to 123.123, repeating. And then I would simplify by subtracting. 999n is equal to 123. N is equal to 123/999. And this would simplify to 41/333, and it's negative. Okay, so that's just kind of a continuation of what we did with the last lesson. All right, simplify, no decimals. Okay, and I think I already did this number. But if I look at this, it ends in 16, which tells me that it's divisible by 4. So if I take this and I pull out a 4, I end up with 4 times 54. And I know that 54 is the same as 9 times 6, which is good because 9 is a perfect square. I break these up. I get 2 times 3 times the square root of 6. So I end up with 6 square root of 6. So this is simplified. Okay. Same with this one. I'm going to simplify this. This 3 out here, I'm just going to multiply it by whatever I get when I'm done. So it's 3 times 125, I know is divisible by 25, and it's 5 times 25. So I break them apart, and I get 3 times 5 times the square root of 5, so 15 square root of 5. Okay, same with this one. It helps if you know your divisibility rules. 4 is an easy one. The last 2 digits, if the last 2 digits form a number that's divisible by 4, the whole thing is. So this one's divisible by 4. And I end up with, if I take 1920 divided by 4, that's 1632, that's 8. So I get 480. And I know that 48 is divisible by 16 and 3. 16 times 3 is 48. So this would be 16 times 30. 30 is not a perfect square, and there's nothing I can factor out of it. It seems like a big number, and because it's an even number, you say, oh, it should be divisible by something. Well, it's not divisible by 4 or 9 or 16 or 25. So 30 just has to stay as 30. So square root of 4 times the square root of 16 times the square root of 30. I have 2 times 4. This gives me 8 square root of 30.